All right. So today we are going to continue talking about local search. And if you think about local search, and just remind yourself where we were, we defined that we want to solve a problem using a local search setting, which basically means we are going to search in the solution space. We will not search in the partial solution space, which is what we were doing in a systematic search setting. We are going to search in the solution space, a complete solution space. And we will artificially define a neighborhood function, which will basically say that two solutions are similar to each other, right? For example, in the context of n queens, we said that my search state is all the queens placed one in each column. And my neighborhood function was I will pick any one queen and move it anywhere in the column. That is what we defined as our neighborhood function. With every local search problem, with every state, we will associate an evaluation function. And in the case of n queens, the evaluation function can be the number of pairs of queens which are not attacking, in which case we want to maximize this particular quantity. And then we defined a hill climbing search, a greedy local search, as our first algorithm, and this is where we stopped. So just to remind you, this algorithm was start from any state, right? Any current state and loop. And in the loop, you look at all your neighbors, all the states, all the solutions which you can reach in one step. Evaluate all your solutions, all your neighbors, pick the best, and that best is neighbor for now. And if value of neighbor is less than equal to value of current, which basically means all my neighbors are worse than me, I stop. But if there are neighbors which are better than me, then I move or jump to the best neighbor, with tie breaks decided randomly. And I repeat. So I am at a point, I look at my neighbors, jump to the best neighbor. I look at its neighbors, jump to the best neighbor. I look at its neighbors, jump to the best neighbor, until I reach a state where all neighbors are worse than itself, or the worse than the middle state, and then I say, done. This is my solution. This is called hill climbing search. And we discussed that it is like climbing Mount Everest in a thick fog with amnesia, because I am climbing, because I am always looking at neighbors and deciding the next best state. It's like a climbing of Mount Everest because I want to maximize an objective function, so you can think of that evaluation function as a mountain. We are in a thick fog because we are never looking beyond one step. We are only looking at one step. This is in substantial contrast to depth first search and breadth first search, where in depth first search we are going depth first and going really deep, then but coming back. There is no such coming back in hill climbing search. With amnesia, because I completely have no memory of how I reached this particular point, right? It's like Gajni all over again, right? Memento. Right? And then we started talking about landscapes, search landscapes. So now this is sort of a schematic which sort of shows you the value of an objective function at different points of the state space. And let's say it was a one-dimensional problem. Of course, no problem is one-dimensional typically, unless it's an artificial problem. But let's say it was a one-dimensional problem, and let's say I was doing local search. So I could always go in two directions, left or right, and I look at whichever is the better direction to go, that is where I go, right? So typically I'm going to climb the hill. And so this is the global maximum that I want to reach, right? But of course, I may not end up reaching this global maximum, I may end up reaching the local maximum, or local optimum. If I'm in a minimization setting, it could be called local minima and so on. What happens? When would I reach local maximum and when would I reach global maximum? What does it depend on? It depends on where we start from. If I start on this hill, I will hit a local maximum. If I start on this hill, I will hit a local maximum. It's a flat local maximum, but it's a local maximum nevertheless. If I start on this hill at left side, I may reach a shoulder and be stuck there, because none of my neighbors are better than me. On the other hand, if I start on this position or this position, then I will reach the global maximum. So as we said, hill climbing gets stuck in local optima, and it gets stuck in local optima depending upon where I start. Okay. Let's look at a simple example. Hill climbing on 8 queens. Now we have to ask, how do I start the process? So we can, let's say, start with a random initialization. Random initialization is every column place the queen randomly, right? So you have placed 8 queens randomly on a column, on each column, and then you start doing hill climbing using the neighborhood function that we defined. 14% of the time it solves the problem. 8 queens is a hard enough problem actually. 14% of the time it solves the problem in 4 steps. In 4 steps it solves the problem in 14% of the time. 86% of the time it gets stuck in a local optimum. It is not a solution. You know that there are some queens attacking, but I can't make another move to improve that particular solution. And when it gets stuck, it only gets stuck in 3 steps. So basically what happens, hill climbing, you start and it either, one of 7 times, either you have solved the problem or you are stuck. But it happens in 3 or 4 steps. Now think about, this is the power of local search and the weakness of local search. On the other hand, if you were doing depth first search or depth first search branch and bound, it will take you a huge tree expansion before you find a valid configuration. Because you will make mistakes early on, and then you will backtrack, and then you will, if you have made an early mistake, then you will backtrack from the full subtree before going to the next subtree, etc., etc., etc. So you will be spending a large amount of time doing the search, whereas in local search, you will zoop, stop. Now, stop with a solution, stop without a solution, but stop. And now what I would like you to think at the back of your mind, I don't want a suggestion right now. What I would like you to think at the back of your mind is, how do I fix this? Can I improve local search somehow so that this 86% failure can be reduced? That is our first job for today. And the typical drawbacks of hill climbing are local maxima, plateau, and other structures which lead you to not reaching the global optimum. So for example, we already defined what a local maxima is. This is one local maxima, this is one local maxima, this is one local maxima, and so on and so forth. Plateau is when my neighbors are not improving, but they are exactly equal. They are regions where not much is happening. I mean, solutions are changing, but the costs are not changing. And then there are many other characteristics, like something called diagonal ridges. Diagonal ridges says you are at this local optima. The only way you can get to the next local optima is if in one direction you make downward moves and in the other direction you make upward moves. Complicated stuff. But in general in life, if think about it, this is actually, you know, this is true for all of us. If you really have to ask, in our life, do we do depth first search, breadth first search, iterative deepening search, A-star search, or local search? What would you say? What is the closest? Now I know that we don't do any of this exactly, but what do you say? Which is the algorithm that we live our life closest to? Do we ever go back in time? Can we ever backtrack our life? We can never backtrack our life. Whoever says you hit a reset button is only making metaphorical statements. The time never comes. The old time gone. We are always leading a life and we are always looking at our neighbors. Neighbors are the one-step action we can take in life. And we jump to that particular action. And we go there. We never backtrack. Neither do we keep track of many different states and keep jumping between them like a breadth first search. Nor do we restart from childhood and go down, and then we didn't find a rich and famous solution, we restart from childhood, and we don't do this. We don't do iterative deepening search. We only lead one life and we only lead our life in one direction. We always do local search in life. And now here is an important thing. It's a simple metaphorical question. If I am stuck in a local maximum and I want to reach a global maximum, what do I have to do? It's obvious. I have to go down. I need to know where the global maximum is. That's a good question. We may have more information, right? So that's why I said we don't exactly do local search. But let's look at the intuitions that local search gives us about our life first. We are stuck at a point. Now this happens in a wide variety of settings. You are writing a paper. This happens to me all the time. We write our paper, there are some issues with it. We improve, there are some issues with it. We improve, we improve, we improve, we improve. We are now stuck somewhere. The paper is not getting accepted. The reviewers don't like it. What is happening is we are stuck somewhere close to the local optimum. We cannot jump to a better solution from here. We have made lots of choices in the way we have structured the paper, and because of which our paper is now at a place where small improvements are not going to improve it further significantly. If we really have to jump to a better solution, what do we have to do? Can you guess? Start afresh. We have to rewrite it. As they say, a wise man writes a second draft. This is true for your code. You start writing the code, you write the code, you're finally done with the code, and then you feel like, okay, I've understood a lot about my problem while writing the code, but now I am sort of stuck. If I have to really do a better job, a more efficient job, a better structured code, etc., I have to start again. You are in a relationship with somebody. You are married to somebody. Slowly you have developed this codependence. The husband takes care of the income tax and the wife takes care of the, whatever. Cooking. I am making, these are stereotypical, I apologize. The wife doesn't know how to take care of income tax, the husband doesn't know how to cook. They are very unhappy with each other. This happens to not cooking and income tax, but this scenario happens to apparently a large fraction of our population. It is said that 5% of people in a marital relationship are happy. I am not making this up. And in the West, we have 49% divorce rates. So, what happens? You have reached a local optimum in this relationship. You are gaining something from this relationship. You are gaining not doing income tax or not doing cooking or whatever it is that you are not able to do, that you have delegated to the other person. But you are unhappy because there is no satisfaction, there is no this, there is no that, the person is blah, blah, blah. Okay? We all have seen many people in our family or friend circles who are in this kind of a situation. In order to get to a better optimum, they cannot start moving up. There is no ladder from the local optimum to the global optimum. The only way you can reach a better optimum is if you first mess up your life even more. That's just the reality of it. Now, intelligence is based on, what do you see long term and how do you trade it off with short term. A lot of people in Indian setup, for example, are never able to take the leap of divorce or separation or anything like that, because there is one person in the family who doesn't feel financially secure or independent or doesn't have the confidence to take these steps. The going down is so much risk for them that the potential reward in the future doesn't feel strong enough, even though they want it. They're never able to take that leap. So in life, be it whatever situation, okay, these are all examples. One more gruesome and gloomier than the other. Writing a paper is okay, who cares? We can write a better paper. But this is always true in life. You always have to take a step back and say, okay, I have reached a certain local optimum. Is this a local optimum that I'm happy with? If I'm not happy with it, is there hope that I will be happier in a different place? Now this is something that local search cannot do, but we as humans can do. And if so, we should be willing to let go of the nicer things in this local optimum, which there are some always. because it's an optimum of sorts. Have to go down. Have to deal with all the repercussion of going down. If I'm starting to write a paper afresh, if my deadline is in 2 hours, that's a terrible idea. But if my deadline is 2 weeks down the line, okay, we have enough time to actually try to fix it and try to do hill climbing. So if to first reach rock bottom, as they say sometimes, you know, there are some people who say that it can't get any worse, I have hit a rock bottom, there's only upward from here, right? It's a sort of famous way of saying from people who are not doing well. But then once you hit that point, then if you start hill climbing, and if you do this more carefully, there's a good chance that you will hit a better optimum. Alternatively, you may reach that optimum and realize, oh man, this is even worse than where I started from. That's also possible, right? So who knows? So you have to be careful. But this is what local search teaches us, that from a local optimum, the only way to go to global optimum is to potentially go down. Okay? With that perspective in mind, let us see if we can fix hill climbing. Let us start with the easy problem. Let us say we are on a plateau. We are on a plateau, which means our next neighbors are all equal value. What is the easiest thing we can do in the hope that we would be able to get over the plateau and do even better? What should we do? Anybody? Instead of saying that my next neighbor should be greater than me, just simply say that my next neighbor is greater than equal to me, which is also called a sideways move. So if there is no downhill or uphill move, allow sideways move in the hope that the algorithm can escape. What is the hope? The hope is that it's only a local plateau. I will keep moving on sideways, and at some point I will hit a point from where I can start moving up again. Sort of the hope is that I will be in the left side of this figure. I keep moving, I reach this shoulder, I keep going on the shoulder, and at some point I reach this corner point where I can start moving up again. This is called sideways move. And for 8 queens, okay, so now the question is, how much sideways move do we allow? Do we allow add infinite sideways move, or do we allow a little bit of sideways move, right? So let's say we place a limit on the number of possible sideways move to avoid infinite loops. Let's say we impose a limit of 100 on 8 queens. Now remember, without sideways move, 8 queens succeeded 14% of the time. With sideways move, 8 queens succeeds 94% of the time. With just this one small change, greater than to greater than equal to, we have a maximum limit of 100 for that. We have converted our problem, which was 14% successful, to 94% successful. There's a little bit of catch. The catch is now it doesn't take 4 and 3 steps to success. It takes 21 and 64 steps to success. So 21 steps for success and 64 steps for failure. Okay? Today in the next class, we will be looking at many different algorithms in this fold. And in fact, local search is sort of very intuitive. So you can start making your own algorithms, and most likely either somebody has made it or there is some problem where this is helpful. So, just think about it that way. Okay? Let's stop here.